Okay. So today is going to be a little bit of an application day. This section in the book on mechanical vibration, I think is fairly long and has a lot of details in it. So I'll probably, I'll probably end up doing some of it tomorrow, and then we'll start on the Laplace transform for that. Okay. So anyway, this setting of problems is called mechanical vibrations. And this is these are some physical systems that are well modeled by the second order linear non-homogeneous ODE that we've been dealing with. So this is usually sort of a simple first model that people will discuss in a calculus-based physics or in a differential equations-based physics or mechanics class. And that's what we really mean by mechanical vibrations, just physical objects moving. It's useful in a lot of different situations, but we'll kind of think of it in the park situation. So we're going to consider how the position of an object evolves in time. So we'll write solutions as y of t, where y is the position of an object. This is just sort of the archetypical example. But we also can consider this thing more abstractly. So this is the position of an object, and because we just have one function in terms of y, this is we think of this as constrained to moving along a straight line because our solutions are one-dimensional. And of course, t will be time elapsed. The t will, because we're thinking of this as a physical system evolving through time, then we'll use the variable t to represent time elapsed. Okay, so we're going to consider three forces acting on an object. So force number one, this will be called the restoring force. Or sometimes spring force, because in most cases we're thinking of this as being a force caused by a spring. And this is a force which acts proportionally to the, how did I write this? Proportional to, yeah. We'll write this as how it's proportional to how far the object is from its equilibrium position. This just kind of means a position where if the object was already there and it had no velocity, it would just stay there. In the example in the notes, or the way they go through the derivation in the notes or in the book, we think of this as an object hanging on a spring. And so there's a force that the spring exerts pulling the object back up. And then there's a force exerted by gravity pulling the object down. And so the equilibrium position will be where those two balance out. So this is how far the object is from the equilibrium position, and we'll think of y equals 0 as equilibrium. So y equals 0 will be the equilibrium position. So if we're thinking this as vertically above the equilibrium position, we'll get positive y, and then below it will be negative y. So this is modeled as minus ky with k greater than 0. And this is, so if we have a positive y, we have a force that is in the negative direction, so it's a force pushing it back down. And if we have a negative y, it's a force pushing it back up. So this force tends to push the object back toward equilibrium. And we kind of think of this as a spring. The further you stretch out the spring, the stronger the force gets. And a way of modeling this is just some constant times the distance. And this is known as Hooke's law, and you may have seen this in a physics class before. It's not real. Well, I should say it's not a perfect representation of the reality of a spring. You might imagine, of course, the spring is this physical object, and it's a lot more complicated than just some number multiplied by how far it's stretched out. But it turns out to be a good enough approximation that it's interesting to think about. Okay, the second one, called the damping force. And this is a force I should have wrote somewhere in that description of the restoring force. It's a force that acts in the opposite direction. But anyway, this is a force which acts proportionally to the object's velocity and in the opposite direction. And so we write this one as minus cy prime. So of course, y prime is the change in the object's position, and so that's the velocity, the rate of change of the object's position. And we'll say c is greater than or equal to 0. So while in this setup, we're going to assume that there is some restoring force, we'll also consider the possibility that there's no damping force. So this is a tends to, the intuitive way to think about this is that it tends to slow the object down. And this is examples of this are EG means for example. So for example, air resistance. So again, air resistance is more complicated than just multiplying a number by the velocity, but pretty close. So air resistance, or you could also think of it as movement through some other fluid. If you, well, I won't go into detail on that. Any more detail than already. Okay, and finally, there is what we think of as an external driving force. So this is a force which we write as f of t. And this is just something else. So this is just we do think of this as a continuous function. It's nice because we can do calculus with it. So it's a continuous function that acts on the object, but it doesn't depend on the object position or velocity or anything else. It's merely it just depends solely on time. So it's just some outside force, perhaps that so maybe you think of something as bouncing up and down in a spring, and every time it gets to the bottom, you kind of tap it, make it go up a little higher. Or you're swinging in a swing and you swing your legs to make yourself go higher. So these are examples of driving forces. They are external and usually controlled by us. Okay. Now, by Newton's law, but it's really Newton's laws of motion. Acceleration, in other words, y double prime, is proportional to the force acting on the object. You might be familiar with the proportionality constant in this law, just like this K and this C here, more commonly known as mass. And in contrast to these other proportionality constants, we do think of this one as being exact. That mass times acceleration is exactly equal to the force acting on the object. So the way we can write all this is on the one side, we will say that this is the mass times acceleration. So this will represent all of the forces that are acting on the object and their proportional relationship to the acceleration of the object. So there's mass times acceleration. And then acting on the object, we have the driving force. We have the damping force. And we have the restoring force. So we get this. And moving these to the other side, what we're left with is my double prime plus cy prime plus ky is equal to f of t. And this is the second order. Describe this thing. It's second order. It's linear. And it has constant coefficients. All of these are nice things. And then it's non-homogeneous, which is possibly not so nice depending on what the non-homogeneous term is. So if it's something that we know how to deal with, we don't know. Now, what we tend to see solutions to this dE that are oscillatory. Whenever we get something that's far away from the equilibrium position, it has a force applied to it that accelerates it in the direction back towards the equilibrium position. it overshoots it and comes back down, and goes back up and comes back down, so on. So we expect these things to oscillate, at least from our physical intuition. But now we have a mathematical model. We'll see how that doesn't be true. Because of this, the solutions are often referred to as vibrations and oscillation, or oscillation. So these are usually the way we refer to the solutions. In a couple of cases, if the driving force is 0, we'll refer to the solutions as free vibrations, free vibrations only. And then in the absence of the damping force, so there's no driving force, the no damping force case is equal to 0. We refer to these as an undamped system. And then finally, a very common name to refer to all of these situations is these solutions are harmonic motion. All right, and just one final note: this is actually a very an ODE that's very rich and interesting. Solutions are interesting and have a lot of interesting characteristics. Okay, so let's look at some example situations. And the first and simplest one is what we'll call undamped free motion. So combining both of those special cases that we saw before, or more commonly, this is referred to as simple harmonic motion, or a simple harmonic oscillator. Okay. So in this case, we'll write our system as y double prime plus ky is equal to 0. And for the sake of simplicity, we're going to rewrite k is equal to omega 0 squared. And the reason for this will become clear in a minute. So we can rewrite this thing as y double prime plus omega. Well, the use of omega and omega 0 maybe is not so clear, but the fact that we're rewriting this thing to square will become clear soon. And we can do this without any worry of replacing our real coefficients with complex coefficients, because we assume k is greater than 0. So k is positive, strictly positive. Okay. Oh, did make one small mistake. So we do think of, I did forget the mass coefficient here. So we're going to write, when we divide both sides by m, so this should be k over m. Not just k. That's a little mistake there. In other words, omega 0 is square root k over m. Okay, the characteristic equation we get for this, I of r, will then be r squared plus omega 0 squared equals 0. And if we subtract, well, let's go through the steps for the sake of whatever. Anyway, subtracting this over the other side, we'll take the square root of both sides. And of course, the square root of that -1 will become an I. And so we get plus or minus omega 0 I. So we get a pair of complex conjugate roots. And this gives us the situation where we have our solutions in terms of sine and cosine. So oscillatory solution. So we have y1. Actually, let's just write out the general solution. We can go straight to that step. So cosine C1 cosine of omega 0 t plus C2 sine of omega 0 t. So we've already seen the derivation of how we come to these solutions, or how we come to these solutions. So again, notice we have oscillatory functions here, so we're going to get oscillatory behavior. Now, in this, writing out this solution here, it might be difficult to see, but we can actually take this entire solution and rewrite it in terms of just a single trig function. How do we do that? Well, it takes a little bit of rewriting and a little bit of trig identities. So the first thing we'll do is we'll declare this constant r. And what this will be equal to is the square root of C1 squared plus C2 squared. So if we think of the C1, C2 as a vector, this is the length of that vector. Or if we think of some point C1, C2 in the plane, then this is the distance from the origin. So when we get C1 over R, I'm going to give myself a little more room. C1 over R and C2 over R, then the point, actually I'll write it like this. The point C1 over R, C2 over R, or the vector C1 over R, C2 over R, is on the unit circle. So we can rewrite C1 over R, C2 over R as sine and cosine of some angle. So let's say that we'll find this phi, so this will be our parameter, somewhere between -pi over 2, pi over 2. We're going to think of looking at the angle starting from 0 going equal amounts in either direction, positive or negative. Yes. Okay. We only need to consider the possibility where one of these things is negative, possibly negative. Okay. So we'll find this phi between -pi over 2, pi over 2. And then such that we get cosine of phi is equal to C1 over R, and sine of phi is equal to C2 over R. Now this allows us to rewrite y. It's right there, but it'll be a little clearer if I just write it again. So plus C2 sine omega 0 of t. We can rewrite C1 and C2 as R times C1 will be cosine of phi times R cosine of omega 0 t plus R times sine phi will be C2 sine of omega 0 t. Maybe I'll put parentheses. Make it a little nicer. Okay, and so if we multiplied through by R, we would just get C1 and C2 back. Now we'll use a trig identity, the sum and difference angle identities, to rewrite this as R times cosine of omega t minus phi. That's using this trig identity. Now in this form, it's really easy to just look at this function and describe what it does. So cosine normally oscillates between -1 and 1. It goes down to -1, back up to 1. So when we multiply this thing by R, we get the largest possible value that this will attain. So this R is the largest value that the solution, or let's say the vibration, let's call it the oscillation. So this is our solution. This is the largest value that the oscillation attains. So this is the largest distance that we go away from the equilibrium position. And that's both in the positive direction and the negative direction. So we know how cosine behaves. R just scales that up. And this is called the amplitude of the oscillation. So how far it goes to the equilibrium position. The period, well, let's say the amount of time. And then we'll introduce the technical terminology. The amount of time it takes for cosine to go through an oscillation. So a full oscillation takes 2 pi. So 2 pi time. So multiplying our t by omega 0 speeds this oscillation up by a factor of omega 0, so that the period, so this is what we were thinking of as the time it takes to go through a full oscillation. That's referred to as the period. This period is t equals 2 pi over omega 0. So the larger the omega 0 is, the faster this omega t goes through that 0 to 2 pi span of time. And finally, the minus phi inside the cosine, it merely shifts where we're starting from. So if we're starting from 0, then subtracting phi from that term will shift it forward by phi. So we have to get to the time phi, or the input phi, before we can say that we are at the 0, the input of 0 to. So that minus phi shifts the normal oscillation of our sped up cosine of omega 0t, to the right by phi. So of course, if phi is negative, that means we're shifting to the right by a negative, which means we're shifting to the left. And this is referred to as the phase shift, or the phase change, or the phase angle. Okay, so that's all terminology. And now we'll look at an example. And the example will require us to know a little bit, to work through a little bit of physics in order to get all the parameters that we need. But it won't be too hard. So let's imagine we have a weight on a spring. And at equilibrium, so when we think that there's no velocity, there's no acceleration, the object is just sitting still, all of the forces are balanced out. Then it stretches, did I spell that right? It stretches the spring 6 inches downward from its natural length. So that's where it gets to the point of equilibrium. Now let's assume the object starts, so this is at time 0, our initial condition. The object starts 3 inches above equilibrium. So somehow we've got it into position where it's 3 inches above the equilibrium, but its velocity is 6 inches per second downward. It's got a negative velocity. Now we're going to assume that there's no driving force or damping force. So this is well, this we'll assume that this is modeled by our undamped free motion, or simple harmonic motion, or simple harmonic oscillator. And this is, of course, a little bit of a deviation from the real world. We're not applying any external driving force, but there's always a damping force, because we know that even if we had a perfect spring and a perfect object bouncing up and down, eventually it's going to stop. And the damping force is the reason for that. Oh, there's also, I'm not sure if this is well modeled by the situation, but there's also a force internal to the spring. There's some amount of energy that's expended as the spring moves upward and downward, simply because of the motion. So it sort of has some kind of internal friction, you might think of it, that it expends some of its energy as heat. And so that also causes slowdown as well. So that could be included in the damping force. But we're thinking of this in the imaginary situation. where everything is sort of perfect. It's in a vacuum. This is the perfect spring, blah, blah, blah. I think in certain situations where we think of an atom as being suspended in this potential energy well or potential field, then this does come very close to approximating exactly how it moves. There are real world applications that depend on this kind of. But the ones involving springs, that's why I kind of am hesitant to use the term spring force for this, because it does actually apply to a lot of other situations. Okay. Now, where am I in my notes? Oh, that's it. That's all of the information that we need in order to determine how this thing is going to move. So how will it move? Well, it'll bounce up and down. We aren't given the spring constant or the mass, so we want to know K and M, but we aren't given them, which is unfortunate, but not a problem, because we can figure out, well, we actually don't need them. What we really need is the ratio, because what we want is omega 0. And that's actually the square root of K over M, as we saw before. So it's enough to know what the ratio is, not to know their exact values. And we can figure those out. At equilibrium, the spring is stretched 6 inches downward. So we're going to have some spring constant. And I have to say, I'm a little bit concerned at the moment about this derivation, but that's okay. We're going to go with it. So we have K times, we'll write delta L, because it's not distance from our equilibrium position. We're at our equilibrium position. It's distance from the normal endpoint of the spring. So the spring is normally like this, and then with weight on there, it's like, so that delta L will be the 6 inches there. And then the force due to gravity is mass times the acceleration due to gravity. Okay, so our delta L is equal to 6 inches, and our G, we're going to approximate by 32 feet per second squared. So this is an acceleration. So the units that we want to be units of acceleration. Now we want to make sure our units match in inches, similar to feet, but they're not exactly feet. So we'll transform this into half a foot. Okay. So now, if we solve for K over M, this is equal to, see, we divide the M over to here, which means we divide the delta L over there, and we get G over delta L, and their square roots would be just the square root. And so we're thinking of this thing as being the square root of 32 over 1/2, square root of 64, which is 8. And what are the units on this 8? Well, this was 32 feet per second squared, and this was 1/2 feet, so the feet cancel out, and we're left with 1 over, give myself a little bit of room, 1 over second squared, square root of 1 over second squared, which gives us 8 per seconds. There's nothing per second, it's just the reciprocal of a second, which can feel a little weird, so we often write this as 8 hertz. The thing that we're counting is actually cycles, but the unit turns out to be per second. Okay, so this is our omega 0. So we've got that, and we no longer need to know what came from because we've got all the information. Okay, so the second order linear homogeneous, in this case it is homogeneous because our driving force is 0. ODE is this. And we know that the general solution of this thing is y is equal to C1 cosine of omega 0 t plus C2 sine of omega 0 t. And you know what? Let's go ahead and substitute 0. Solution by erasure. We'll go straight to that step, and we can do that. Now, when we multiply this 8 per seconds times t seconds, we get a quantity with no unit at all. Interesting observation. But we don't have a good idea for what unit we would feed into cosine and what the resulting unit would be when it came out on the other side. So we feel okay about that. Okay. Now what do we do? We want to figure out what C1 and C2 are, and it's pretty easy to. I need to leave my initial conditions on the screen. Okay. Back. We're going to figure out what C1 and C2 are based on our initial conditions. And actually, in this form of the solution, it's pretty easy to do because we have y of 0. Well, remember what y of 0 was. This was the object starts 3 inches above equilibrium. Since we're trying to do everything in feet here, I'm going to write that as 1/4 feet. Actually, let's put the unit in. It's always interesting. Well, it's interesting for a certain definition of interest that how these things work out. So if we're thinking that these cosine and sines, the thing that goes in has no units, the thing that comes out has no units, then where does this feet come from? So we have y of 0 equals 1/4 of a foot, and if we plug in 0 on the other side, we get C1 cosine of 0 plus C2 sine of 0. And this is just 0, this is just 1, and so what we're left with is just C1. So in fact, it's the C1 itself that carries the units of length in this case. We get C1 is equal to 1/4. We write out the equation. We never put the units in the equation. They're sort of implicit. Okay, and y prime of 0, well, this was the velocity, and the velocity was 6 inches per second downward. So this is negative 1/2 feet. And when we work out the derivative, we get C1 times the derivative of cosine of 8t. Well, that's just negative sine of 8t times 8. So negative 8 C1 sine of 8t plus. Same thing happens here. Sine is going to go to cosine, positive cosine. By the chain rule, an 8 is going to pop out into the front. And we'll get 8c2 sine of 8t. At 0, this one goes to 0, which I could have written it like I did before, but oh well. What did I do? I wrote sine instead of cosine. My bad. This one goes to 1 because it's now cosine of 0. And what we're left with is 8C2. Now, if we think of C2 as having the whole punchline was going to be the units work out, but I didn't write the units right. Y prime is a velocity, so this should be feet per second. So, okay, now on the other side, what we should get is feet per second. And we think of the C2 as having units feet, but then there's this 8, and this was the 8 that was inside here. And remember, that was the omega 0, which had units per seconds. So the unit that we get overall is, in fact, feet per second. And so our C2 ends up being what? What does it end up? It ends up being C2 is equal to, go ahead and highlight this so I don't lose it. C2 will be negative 1/2 divided by 8, so negative 1/16. It'll be negative 1/16 feet. So all of our units work out. There's our C1 and C2. And you see why it's in this form. It's very easy to get because the derivatives, the initial thing in its derivatives give you a 0 and a 1, and a 1 and a 0. Think back to unit vectors from Calc 3 that might sound familiar in 2 dimensions that we get our unit vector, our perpendicular unit vector. Okay, so we figured out what C1 and C2 are. And so now we can write out our solution. Next step. 1/4 cosine 8t minus 1/16 sine 8t. Now, once we have this, we want to take this and transform it into the phase angle form or the phase shift form. And in order to do that, we'll just compute what our r is and our phi. I think maybe an interesting way to think about this is we take our C1, C2, which, as we saw before, we thought of as being parameters on these two things that are perpendicular to each other. One of them was 1 while the other one was 0. And then when we looked at the derivative, one of them was 0. So these are almost, there's sort of an analogy between these and rectangular coordinates. When we swap to our other system, of course, we have to have 2 parameters. Those parameters end up being r and phi, which suspiciously look like the parameters that we have in polar coordinates. We're doing something very analogous to that transformation. Anyway, our r ends up being, okay. We have just enough time to finish. So our r is square root of 1/4, that's our c squared, plus negative 1/16 squared, which is 16 squared. And this is equal to, it ends up being equal to square root of 17 over 16. Not particularly difficult to see, but nonetheless, that's what we get. Okay, so well, I'll indulge my fascination with how the units always seem to work out. The C1, we're looking at C1 squared, so that C1 is in feet, and so C1 squared will be feet squared. So we have feet squared plus feet squared. Square root of that, well, that's just feet. So maybe I should write this in a different color because we don't write these things out in the formulas. But if we go through the analysis of the units, everything works out. So remember, this gets multiplied in the front, and this is, we think of this as our amplitude. And the amplitude really is a measurement of distance from the equilibrium position. Okay, now to get the phase shift, we'll notice that we can write tangent phi as sine phi over cosine phi. And this is equal to, well, sine of phi was C2 over R, and cosine of phi was C1 over R, so this equals R over C1. And what we're left with is C2 over C1, which is again a dimensionless constant, no units. It's feet divided by feet, so it's just a number. Okay, so C1 over C2, what was that? That was C2 was negative 1/16, and C1 was 1/4, so the reciprocal is 4 over 1. And what we get is negative 1/4. And so to get phi, we'll just take the arctangent of both sides, negative 1/4. And what we get for the arctangent of negative 1/4, consulting my notes, is approximately negative 0.245, I think. Unless I made a mistake writing that, which I don't think. Anyway, that's good enough, so we'll just say it's equal. But this is the phase shift. So we're taking this oscillation and we're shifting it to the left by 0.245. Dimensionless units of cycles. So we're shifting it by that much of a cycle. And our period of oscillation, so the period, well, this was our phase shift. This was our amplitude. Okay. And then our period, nope, not how you spell period. So the period is 2 pi divided by omega 0, and omega 0 was 8. We get a period of 5/4. Here, here, here. And of course, what we have is this 2 pi was a dimensionless constant, and this omega 0 was per seconds. So when we divide by per seconds, we get seconds. And so the period turns out to be a unit of time. Nice. Okay, so that's that example completely described. Based on these three quantities right here, the amplitude, the phase shift, and the period, we have completely described what this simple harmonic motion would be. So that's completely determined. Now, the next thing we would look at, and we're not going to look at today, but we'll just preview because we have about 20 seconds left, is the case with the a driving force. So we'll call this driven or forced harmonic motion. And this is when we have, and we're also thinking of this, we're still going to look at the undamped case. So this will be my double prime plus ky equals some driving force. And we're going to assume that this driving force is also oscillatory. So there's an outside oscillation that's sort of also pushing on this thing. And so we write this as F0 cosine of omega t, where this omega is the period or the I'm trying to think of the frequency of this oscillation. So this is the driving frequency. Anyway, that's I think that's enough for today. And yeah, good enough.
Yeah, this stuff makes more sense to me. Like the more the physics stuff.
Okay.
I don't know. It just makes more sense in my head, I think, than some of the other stuff.
It's helpful to kind of attach these things to a picture of what's going on.
Yeah. Well, I'm also an engineering major, so I think that part of my brain is just a little bit more wired for this than like some of the other stuff in this class.
You have some practice.
Yeah.
Well, with this
I need
class,
some, yeah. I need some help with let's see, what the undetermined coefficients.
okay.
Because I was working on the homework yesterday and I spent a lot of time on it and did not make a lot of progress.
Okay.
So like I read a lot in the book. I tried to like watch some videos of examples, like I rewatched our lectures and stuff, and I'm still struggling with it. I'm not sure if there's like what I'm missing with it.
Well, you know, it's just a matter of practice. So we can take a look at this problem. Do you have it or
Okay.
probably, did you say it's on the web work?
Yeah. What I'm struggling on is 4. It's just finding a particular solution.
Okay.
I can read it off for you.
Wait, is this homework 3?
It's homework 6.
Well, we're really, wait, should we be that far ahead by this point? Okay. I'll trust the schedule. So which
I
problem
don't know. It says it's due. Yeah, it says it's due tomorrow.
Okay, I may have to adjust the timing on this a little bit, but which problem is it?
It's number 4.
Number 4.
I've reworked it many times and I've used the undetermined coefficients and I used variation of parameters and I still can't get it and I'm not sure what I'm missing.
Okay. So let's take a look at this. So this is equal to minus d e to the 3t. Okay. And so if we use the method of undetermined coefficient, then there's this step of eliminating the exponential. I can get rid of this now. Go back. It's just weird for me to talk and not see who I'm talking.
Yeah.
So there's this step of eliminating the exponential. So we're going to look for a particular solution of the form u e to the 3t, and we're figuring out u. The characteristic polynomial is r squared plus 4r plus 3. And this does say we're just looking for, yes, just the particular. Anyway, this is 2r plus 4. And I'll go ahead and just for the sake of reference, I'll write out that alpha is equal to 3. So, well, I can go ahead and compute what pi of alpha is. So that's 9 plus 12 plus 3 is 24. And chi prime of alpha is equal to 6 plus 4, which is 10. So what we're going to get is this other ODE in terms works out like this. And that factors nicely, so that's good. And what we get is this is equal to minus t. And so what we're going to do to get a particular solution to this, well, I guess we don't need, okay, what do we need? We need a probably help if I wrote this correctly. Okay, so we're going to look for u's in the form, well, just a linear. So that's going to make our life a lot easier. So AT plus B. This U prime is, U double prime is just going to go away. And so what we're going to have is 10A plus 24A D plus 24B is equal to T. And so we get 24A is equal to 1. And 10A plus 24B is equal to 0. And for the sake of my, we'll write this as 5A plus 12B equals 0. Divide by 2. Okay, so up to this point, do you agree with what I've done?
Yeah, I think the part I'm struggling on is getting the U is equal to AT plus B. So why are you ignoring like the U double prime?
Oh, so I'm not
Why is
ignoring.
that not something that's factored in?
Okay, good question. So what I want, I have my U here in my equation. This isn't one of the situations where my lowest order derivative is some derivative, right? It's just the U by itself is the 0th order derivative. So I know that if I plug in a linear into this expression, I'm going to get a linear from this one, right?
Mhm.
And then I'm going to get a constant from this one because it's going to be the derivative. This one is just going to be 0
Okay.
because it'll be the derivative of.
Okay.
So yeah, I'm not really ignoring it. What I'm doing is just noticing that I don't have to write it. I didn't write a 0 plus.
Okay.
That's the only thing that I'm doing there. But the reason that I picked this is because I want it to match the degree of this. I want this whole left-hand side, the degree of this to match the degree of this. And I know that will happen with general linear because I have this U here already. And that U, that term will be a linear. The other terms will be lower degree, but that's okay. Because at least as long as I have the full degree somewhere, it'll be okay.
So if the T had been raised to like the second power or something, then your U, it would be like A to the T squared plus BT plus C. Is
Yeah,
that
exactly.
okay? Okay. That makes a lot more sense. Thank you.
Yeah. And that's the only thing is that I just want this to match. That's all I want. So if we oh, I should maybe make a point about that is that if we pick a degree that's too low, then when we try to solve our system of equations, we won't be able to get a solution. We'll have no solution because we'll have a 0 for our leading coefficient and it won't match with the non-zero side. So
Okay.
if we pick the degree too small, it won't work. If we pick the degree too big, then what we'll end up with is a bunch of coefficients that aren't determined at the end, and we can just pick whatever we want for them. So we'll end up
Okay.
zeros for those, and what we'll have is we'll end up with a polynomial at the end that has the same degree as the one that we're trying to get to begin with.
Okay.
So it's just as long as we pick one degree that's high enough, it works. So we pick one that's exactly. Okay, so now what we have is we just get A is equal to negative 1/24th. And so that gives me negative 5/24 plus 12b is equal to 0. And now I solve this. Let's see, 12b is equal to 5/24th. And so b is equal to 5/24 times 12. That should be 5/288. 12 times 12 is 144.
Yeah.
Okay. Nothing impressive. So I get u is equal to -1/24t plus 5/288. And so my particular solution should be, well, I'll write it again. All of this times e to the 3t should be. Now let's see what this thing has to say. How do you write e to the 3t? Just e 3t?
You have to do E and then like the little caret,
Okay.
and then you have to put 3t in parentheses, or else it won't see the t. It's really annoying at times.
I agree. I don't really like web work, but I should say this. I don't like web work, but I really don't like grading.
Gotcha.
So, anyway, that it said that was correct. So
Okay.
follow that under.
That makes.
I shouldn't have said out loud.
You're fine. No, because mine's different than this anyway, so I'll just like rework it. So that's the part I was struggling with was getting like the AT plus B thing. Okay, that makes a lot more sense. Thank you.
So, yeah, the first thing is make sure the polynomial degrees match,
Mhm.
and then you just set up your system of linear equations.
Okay. Also, WebWork was using a term specific solution. That's not the same thing as a particular solution, is it?
Yeah, it's again, it's this kind of thing where we're using everyday words with technical meaning. And so particular solution means one solution to the non-homogeneous version of the equation.
Okay.
And specific solution, they mean you take a general solution, so your particular solution plus your general non-solution, and then you solve for those coefficients using your initial condition.
Okay.
So
That makes
yeah,
sense now.
you have a solution before your initial condition,
Mhm.
and then when you apply your initial condition to get it completely stapled down, then you get a specific.
All right, that makes more sense now. Thank you.
But
Have a good rest of your day.
I'll do my best. You too.